Hi and welcome back. In this video we're going to be looking at the first of our bonding topics, which is metallic bonding and the metallic bonding model, how that relates to the structure of metals. So let's get straight into it. This is the key knowledge that we need to know for this unit. In this first video, we're going to deal with just the first 2 points here, which is to describe the bonding in metals using the metallic bonding model, and to be able to draw a labeled diagram to describe the nature of the metallic bonding model. So then from there, we will move on to the properties of metals that arise due to this model. This may seem familiar. It is actually not that much of an extension beyond what you would have already done in your middle years and year 10 science courses. So let's get cracking. So when we're talking about substances in terms of their structure and properties, it's really important for us to understand the nature of bonding, that it exists between atoms in a molecule or a compound in order for us to predict the way they will behave. So essentially what this is saying is that the type of bonding between atoms determines the overall properties of the substance. Okay, so if we know what type of bonding it has, we can make some predictions straight away as to the type of properties that we would see for the substance if we wanted to use it. So being for a building material or an insulator, whether or not it would be flexible, moldable, those kinds of things. We can start to make predictions as material scientists, which chemists often are, as to how these substances will behave. It's important to remember that all bonding is electrostatic. That is, it arises due to the attraction between positive and negative charges, remembering that opposite charges attract while like charges repel. So this is the situation that we want to set up in order for a chemical bond to form. All chemical bonding arises because of electrostatic attraction. It's just the nature of those positive and negative charges that changes, whether or not it's attraction between the nucleus and the electrons, cations, anions, those kinds of things. What that attraction is between is what changes, determining the type of bond, and we need to pay attention to that as we go through. So we'll see this grid a few times, but essentially whether or not something is a metal, non-metal, or combination has an effect on the type of bonding that we see. Metals, which always undergo metallic bonding, okay, is when we have bonds between purely metallic substances. So this would be aluminium, iron, copper. In those pure elements, we see metallic bonding, but also in alloys like brass and nickel alloys and things like that. Anytime there's only metals, we see metallic bonding occurring. When we have only non-metals, we see covalent, and then metal and non-metal, we see ionic. So this is the section that we're focusing on at the moment, and that is the attraction between positive ions and negative delocalized electrons, meaning that we have free moving charged particles, and these substances will conduct electricity, which is why we use metals for wires. So let's move forward. Metals make up the majority of the elements in our periodic table. Okay, you may remember from when we looked at the periodic table and different properties and trends in there, that metals have low ionization energies and low electronegativities. The lowest ionization energy and the lowest electronegativity being that of francium, making it the most reactive metal. Okay. Because they have the same type of bonding, they exhibit similar properties, and common properties in metals can include things like malleability, ductility, conductivity, the fact that they have crystal structures, which we will see more in our next experiment. But primarily we know that metals will, by definition, be an element that lose their outer shell electrons in order to become stable, to gain that stable 8 electrons in their valence shell, or a complete octet. So they will generally form positive cations whenever involved in bonding. As we said, that these are the properties of our metals. There are more than 80 metallic elements, and they vary in how metallic they are according to their position in the periodic table by how easily they lose their electrons. These properties are common between most metals. There are some exceptions. And I'd like to draw your attention here to this formula that we have for density. You may have seen this before, but when we talk about the density of a substance, okay, we're talking about the amount of mass in a given volume. So you may have seen that the density of water is around 1 gram per milliliter. So it would weigh a mass of 1 gram for every 1 mil that we have. Different substances have different densities. So lead is a very dense metal, okay, whereas something like a marshmallow would be very undense. It's full of air, very little mass in a large volume. So if we look at these, we can see that although metals have similar properties, there are variations in them. Some metals have melting points as low as minus 39 degrees, which is mercury, one of our exceptions to metals being a solid at room temperature, right up to metals that have melting points above 1500 degrees. So when we say they have similar properties, we're not saying that they all have exactly the same property. It's just that they exhibit these things to differing degrees. Metals are incredibly useful in our society. We use them in a large number of applications, making use of a lot of the properties that they have, such as being heat conductive or electrically conductive, strong, and lustrous. So if you think about iron, we've seen this used in cookware for years, converted into steel for building applications. Aluminium we see used in aluminium foil and used in aluminium cans, so it's lightweight but strong. Titanium we see in surgical applications and in some space applications and things like that. Gold, of course, we see used for jewelry and things like that, same with silver, because it's highly non-reactive, very attractive and shiny. So because of their diverse array of properties, metals are used for a number of different things throughout our society. Some just aesthetic for the sake that they look pretty, others for their structural or conductivity properties.
Generally, we break metals down into the main group metals or the transition metals. Transition metals we find in the D block. So you'll remember this from your periodic table. We're talking the metals within the D block here. So these are our transition metals. Okay, you may remember that these have an unfilled D subshell. Okay, so that unfilled D subshell gives them unique properties. They tend to generally be harder than main group metals, the main group being group 1, 2, and 3. Okay, and they tend to have higher densities, melting points. Some exhibit magnetic properties, and they have high tensile strength, so they can be drawn out into wires and various other applications like that. The other thing about transition metals is they tend to form highly colored complexes when they form compounds with other elements. So you'll remember one of these being copper sulfate, and that copper sulfate is bright blue. So transition metals tend to be highly colored. So this higher charge to size ratio of the transition metals allows them to pack closer and increases the strength of the metallic bond. If we look at the structure in terms of properties, we can see that the structure gives rise to the properties. So we talk about the fact that metals have charged particles that are free to move, so this allows them to conduct electricity. The forces between the particles must be able to adjust when they are moved, because when we hammer them, we see that they are malleable or ductile. Metals generally have high densities, which tells us that the particles must be closely packed because they have a large amount of mass in a small volume. They also tend to have high boiling points and temperatures. This tells us that the forces between particles must be strong. A large amount of energy needs to be applied in order for us to cause them to melt. And then, of course, metals are lustrous, which tells us that when light hits them, that light is reflected. All of these things lead to evidence that is supported by what we refer to as the metallic bonding model. In X-ray studies, when we look at metals, we can see that they occur as crystal lattices, that is, highly organized structures. If you think about how fruit is often packed in the supermarket, remember you've got these alternating rows of round spheres. And that's how the cations in a metal stack. So within these lattices, we then have delocalized electrons. So the metals, remembering that a metal is still neutral, okay, but the electrons are no longer fixed around the cations all the time. They tend to move freely throughout the lattice of cations, but the overall charge remains neutral. So these delocalized electrons are freely moving through the lattice, but keeping it stable and strong in all dimensions. So if we look at this, this is showing our electrons buzzing around and moving between the cations. The cations are in a regular three-dimensional array. Okay, so if we consider sodium, we put the sodium cations in the positions along the lattice. They occupy fixed positions. They are not moving, but the electrons are constantly moving throughout them. Okay, so it's the electrostatic attraction. Remember, we talked about the electrostatic attraction between positive ions, such as the sodium ion or magnesium ion for metals, and the delocalized electrons. This force extends throughout the entire lattice, so it's very strong. You need to be able to explain each of the properties with reference to the metallic bonding model, so what aspect of the model gives rise to those properties, as well as being able to draw an annotated diagram of the model itself. So this is the kind of diagram that you want to be looking at. Okay, because we know metallic atoms have low electronegativities, they will easily form cations. Typically, as an ion, the cations have localized electrons, but they donate the valence electrons to the delocalized C. All the rest of the electrons are localized around the cation. So if we consider sodium with a 2-8-1 electron configuration, this one electron will be donated, okay, giving us sodium plus, but in the other 10 electrons will still be localized around that central nucleus, with just one of them zipping around throughout the lattice. Okay, so we would draw this as a stacked arrangement of positive cations. If you know the metal, then you should state what the metal is. So if we were drawing a lattice for aluminium, we would draw them as aluminium 3+ cations throughout the lattice. Okay, every aluminium atom would be donating 3 delocalized electrons to the lattice, indicating why aluminium is so strong, because it's got 3 delocalized electrons and all the cations are +3 small aluminium cations. So we have a strong electrostatic attraction between the +3 and those delocalized electrons. So when we want to look at the charge on the cations to draw the appropriate lattice for the metal that we're looking at, okay, we essentially want to determine what the cation would be, remembering that group 1 will always form +1 cations, group 2 will always form +2 cations. So if we were drawing a magnesium lattice, it would look like B here, and we would make sure that we include the symbol of the atom in our diagram as well. So if we have a look at this and we want to suggest different metals for each of the lattice structures shown, in this case it is a +1 metal, so we could be looking at anything such as sodium, it might be lithium, it could even be potassium. Whereas our +2 could be copper, or it might be a group 2 metal such as magnesium, or it might be calcium. +3, there are transition metals that form +3, so it might be iron, but we could also see it being aluminium as well. And I will leave you to find the third one by referring to your periodic table. So that's it for the structure of our metallic bonding model. Remembering that you need to be able to draw a diagram illustrating the array of the positive cations, indicating the delocalized electrons that are throughout, and no diagram is complete without annotations. So being able to indicate the delocalized electrons and a three-dimensional array of metal cations. I hope that has all made sense, and I will see you in class.